And your question is, what do you think makes up the largest gap between theoretical thermodynamics and real-world applications?
Hi, my name is Samantha, and my question is, what do you think makes up the largest gap between theoretical thermodynamics and real-world applications? So in theoretical thermodynamics, we tend to make a lot of assumptions. For example, if we're analyzing a process or a cycle, we might say that our working fluid is an ideal gas. We might say we're operating under steady state conditions, and that the properties are uniform. But in the real world, we might have non-uniform temperature and pressure fields. It might be a transient process, etc. Other assumptions that we make, we often neglect losses due to like friction, or we might assume that a process is adiabatic, meaning the insulation is 100% perfect, which is probably not something that's going to happen in real life. We could also assume that a process is reversible, which of course never happens in real life because all processes have entropy generation and therefore losses, and therefore are less efficient in real life compared to the reversible. So another example of like a gap between theoretical and real world applications would be like in the Brayton cycle, a GT engine. The thermodynamics theory might tell us that we have to increase the inlet temperature of the turbine to increase the overall efficiency. But we have to consider more than just the thermodynamics alone, since under like high temperature applications, even the high performance like super alloys that they use for turbines might crack or deform or have creep with the high temperature. So it's not just a thermodynamics problem alone in the real world. So overall, I think the largest gap would be the assumptions that we make and the fact that we have to consider other things like material limits and refer to other subjects like material science and strengths for real world problems.
And then do you think this gap is getting smaller with better tools or staying the same?
Getting smaller, of course, because like when we make assumptions or assumptions that really affect the problem, it's mostly just when we do hand calculations, but like with simulations, we can simulate like a like I said, non-uniform pressure and temperature fields. We can put that in a simulation, I guess. So it's getting better.